no appreciate you being here. Chime in if you have any questions. We're not going to have a whole lot of problems this morning. It would be, if it gets to 30 minutes, that'd be a long video lesson. But okay. We're doing 45 through 50, and really I think you already did 45. That was in the previous lesson. We're going to go right to 46. And really, a lot of these, 46 is this way, it really helps to have some creativity in setting up your window and setting up the equations. And that's exactly what this one is here. Basically, you're going to try to set this up so you have the real world situation. So right now, the parametric equation, we're going to have these parametric equations here on the left. This one is going to be x equals, we take our feet per second, so 45 feet per second, times, how do we account for this angle here? Well, it's going to be cosine 44 degrees, and times t. And what is our y going to be here? Well, you're starting off at a height of 5 feet, so I'm going to put 5 plus 45 sine 44 degrees t, and we have influence due to the force of gravity, minus 16t squared. So that's that equation from the left. Now from the right is going to take some more creativity, because you have 78 feet between them. So this is where the thing is going. What you're doing is you're starting out at 78, and from 78 at the right times cosine of 39 degrees, and we're going to have times t. Now if you want to get clever with this, you could make this as 180 degrees, so you can go like this and make this plus 41 cosine 141 degrees. You could do that instead, but I think just using the negative like here would be probably the easier way to go. And then y is going to be equal to 5 plus 41 sine 39 degrees t minus 16t squared. So now we can just go to our calculator, and here it is. Let me clear that out. Make sure of a couple things. One, that we are in degrees, and two, that we are in parametric mode for our functions. So here we have it. So the first thing we have here is 45 cosine, and we see we're in degrees here, and that's going to be 44 degrees times t, and then for our y equation we have 5 plus 45 sine 44 degrees, t minus 16 t squared. So that's going to be it. And you can just go back and forth and double check, make sure you have it right. Now here it's going to be the same thing, but the numbers are going to be different, obviously. So 41 and 39 are the key numbers. So 78 minus 41 cosine 39 degrees. Something's happened to my feed underneath here. Didn't mean for that to happen. 39 plus 41 sine 39 t minus 16 t squared. Okay, that all looks pretty good. And when we graph this, this is what it looks like. I don't see a whole lot here, so I'm going to go ahead and change the window. The time of the window will probably be pretty good, and I'm going to change the t step to 0.01 for 1/100th of a second, and our x minimum from 0 and our x maximum is going to be 78, because that's the far right. And then x scale 1, that doesn't make any difference. And y minimum, we can start at 0 and we can go up to a height of maybe 40 feet. I don't know if that's good there. Okay, and we graph, we see what it looks like. So we have the one from the left showing up this way in blue, and the one from the right should show up here in red. There it is. I was getting a little nervous. And so what the graphs of these do not show us right now is the time element of them. So what we're looking for is where the time is this, when the time is the same, where are they closest together? And so to do that, you can go to trace, and so I'm tracing to the right. Now, obviously 1/100th of a second takes a long time to trace, but then I can change to the red one, the one from the right, by going to this up arrow. So at this time of 0.24 seconds, this is where the ball is here on the red one, and then this is where this ball is in the blue one. So these are getting closer and closer together. So here we are at 1.11 seconds. Okay, so they're getting closer, but they're still not quite there yet. So I'm going to go back here and just go to the right some more. Yeah, so 1.21 seconds, and then down like this. Okay, that's pretty good. X is 39.44, and up here X is 39.16. That's pretty close. So really, I think we can experiment around with that, but that's going to be about as close as we can get. So let's just find, we'll go with this 1.21 seconds, and here we are. The higher one from the left is 19.4 feet high, and then this other one here, I scroll down, 19.4 minus 12.8. So we have 19.4 minus 12.8 equals 6.6 feet apart. And it says what find the minimum distance, and when, okay, that's the time, and t is equal to 1.21 seconds. So those would be our answers for problem number 46. Okay, next. 47 was the yard dart problem, and really what this looks like, because 48 is related to this one, is you have a target that is 20 feet from the front edge. So you're 20 feet away. You have a target here like this, and this is 20 feet away. And you're taking this dart that's thrown initial 3 feet above ground. It goes like this, and I think in this particular problem we are short of the target, but the equation is going to be, it's 30 feet per second, so x equals 30 cosine 70 degrees t, and then y is equal to 3 plus 30 sine 70 degrees t, 70, let me see, minus 16t squared. And so what we're doing, and we fall short of the target on 47, but here on 48 we have the same type of situation, but we have 25 feet per second, so x equals 25 cosine 55 degrees t, and we have y is equal to, what is our height? This case 4 feet above. Now that's going to help us get to the target, right? Because it gives us more horizontal distance to work with. So we'll go 4 plus, and we have 25 sine 55 degrees t minus 16t, changes in the variables, and you see what happens differently. That's what we're talking about here. And we know the front of the target is how far away? Front of the target is 20 feet away, and we have a target with an 18-inch radius, so that's going to be 3 feet in diameter. So we just need to get to 23. So let's go to the calculator. Okay, we come here, and I'm going to clear out everything. Okay, and so we have 25 cosine, and let me make sure, I think it's 55. Yeah, 55 degrees is what it is. T, and down here we have 4 plus 25 sine 55 t minus 16t squared. And so if we graph that, this is what it looks like in blue. So we can probably see this enough. Let's shake our window. I'm going to change the window a little bit There it is. Okay, t-step will keep the same. But x maximum, I'm going to go to 25 feet. And we go to, I think everything else, we can go to y max. I can change that to, I'll change that to 25 feet as well, I guess. Okay, and graph. If we set our y scale at our x scale at 1, and it is set at 1, we can graph, and we can see, because we set it 25, so 25, 24, 23, 22. So it looks like we're hitting right about 21, and the front of target will be at 20. And we go to trace, and just go to the right here. We see the path of the yard dart here. So here we are at 20 feet and we haven't hit the ground yet. So yes, it will hit the target. And yeah, so this is right almost at 0. So we're about 20.78. So 79. So we're almost at 21 feet. So yes, hits ground about 20.8 feet, or 20.8 feet away. So yes, hits target. Okay, so that would be our answer here. Okay, and yeah, 49 is another one of those baseball hitting problems, like 44, 45, and so on. 50, hitting golf balls. Nancy hits golf balls off a practice tee with initial velocity of 180 feet per second with 4 different clubs. How far down the fairway does the ball hit the ground if it comes off the club, making the specified angle? So really we have the first one is x. I'm going to call this problem A. X equals 180 cosine 15 degrees t, and then y is equal to hits practice t, so we're assuming that's right off the ground. So we have 180 sine 15 degrees t, and it's going to be minus 16 t squared. So that's really going to be it. And so with all these successive letters A, B, C, and D, all you do is go and change the angle. Otherwise it's the same. So we go to the calculator and put in (180) cosine 15 degrees t, and then down here we have 180 sine 15 degrees t, minus 16t squared. So we just graph looks like this because we really don't have the window set up right for the total flight of the ball. So in this case it might take the ball longer than 6.28 seconds. So you can change that to 10 seconds. It might be helpful to you. Again, our X max, we can go several hundred feet away. I think it has to be 900 feet away. Now, there's a downside of doing it the way I'm doing it here, and that is when you go at 100th of a second, it can take a heck of a lot of time to scroll, but you can just mess with that. I'll go to a maximum height of 200 feet, I guess, and we'll leave it like that. So there we see the flight of the ball. So it looks like we have it set up with looks like it hits those tick marks on the X thing. So let me see what the window says here. So our X scale is 100 feet. So just going to the graph, we know we're about 100, 200, 300, 400. We're about 500 feet out. So just going to the trace to get a more precise answer, we go to the right here, and again, I'm only going at 1/10 of a second, so that's really gonna, it takes a little while to scroll here. But then the upside is we get a more precise answer. Now if I left this time at 6.28 seconds, that would have been plenty of time anyway. But so our height is 9 feet above ground, 8. So you look for y equals 0, or as close to 0 as you can get. Negative. So 0.07, yeah, that's less than an inch off. So 506 feet, 2.91 seconds. So 506 feet. And that's going to be 2.91 seconds. And what I'm going to do is, I'm not going to do all these, but I'm going to just go straight to part D, and I'll leave it to the viewer to do your sensitivity analysis in B and C. So D is 30 degrees, so all I do is go back here to the function editor, and I'm just going to change this 15 here to 30. Do you know what angle it is that's going to get the maximum distance? That's just a question. I don't know if any of you have an answer for me. That's a good thing. You can try that. Anyway, we press graph. This is what we get. So we get definitely a much higher flight of the ball, but much farther out too. So we go to trace. There we are. So again, it's a little weight here. I hope you're having a good week. After we get done with this, I'll give a brief message about what we're going to be doing probably for the rest of the school year. So already X is 600 feet away. So definitely this golf drive gets a lot farther out. What does this equation not take into account? Drag because of air resistance. You might cover that fit. So here we're getting close to ground. I'm looking for the y over here as I scroll to the right, looking for it to get close to 0 as possible. So negative 0.45 feet, and then 4.4. So 876 feet away is what it looks like. So 876 feet away, 5.62 seconds. 876 feet. And 5.62 seconds. Yeah. So this is x is equal to 180 cosine 30 degrees t. And then y is equal to 180 sine 30 degrees t. Minus 16t squared. So if you have any other questions for me, just come up with them right now, because I'm going to drop off here in just another minute or so. Okay, good. Well, then we'll call it a morning. We'll be working on polar equations and polar coordinates starting next week. That'll probably take us through the rest of the school year. Bye for now.